Thank you very much. First of all, I want to thank the organizers for the invitation and you all for being here now. I'd like to start this talk by saying that the neuroimaging is an extremely powerful tool in neuroscience that may give us a lot of biomarkers that can be obtained in an easy, cheap, and non-invasive way. However, there's a however. So this talk deals with the however. If I show you that image, and even though you are not, you don't have a background in radiology, probably you are. It's very easy for you to tell me what's going wrong there and what's the problem of that patient. It's clear one of the legs is broken, and we don't need any number to see that. If I show you this other image that corresponds to an fMRI in rest and activation state, probably none of you can tell me what's the difference between those two images. And this needs quantitation. So quantitation here is not just a way of giving an objective assessment of something we are seeing in the image. Here it means that without the quantitation, we don't have anything. So we need the quantitation because differences are so subtle that we need necessarily to use advanced techniques in order to see what's going on there. Unfortunately, the processing we have to do with images is really, most of the times, very complex. So this is one of the simplest things we can do. This is an SPM pipeline, and here we have to realign the images. We have to pre-process by some smoothing. We have to apply several statistical assumptions in order to finally obtain something which is like this. It's a very nice image, colorful, in which you see things very clearly. So one of the problems of this type of images is that it's a well-known phenomenon in psychology that pictorial information seems very reliable to humans. We are visual animals, and if I show you something, you look at those colors and you say, okay, results is there. I'm seeing very clearly those red areas, so this is something rock solid, okay? But that's quite wrong, in fact. So actually, in engineering and image processing, we call this type of representation false color. So there's something false behind that. The problem is that in order to obtain these colorful and funny images, we have to obtain some numbers, and this image actually is called parametric image, so it means that we are mapping one parameter. And that quantitative parameter may come from different things. In case of we are studying anatomy, for instance, maybe volumes, maybe shapes, maybe textures, may be related to white matter properties, as for instance, direction of the tracts or anisotropy or whatever. And it may also represent function parameters as glucose metabolism, density of neuroreceptors, blood flow, etc., etc. So there's a huge number of modalities of image I can use, and there is another huge number of quantification algorithms that may obtain those quantitative numbers that afterwards are represented as funny color images. Actually, the number of procedures I can apply is definitely huge. So there are many of those algorithms are grouped into packages, and those packages, most of them are free and can be freely downloaded from the internet. And in many cases, they include similar steps, as for instance, registration, segmentation, smoothing, but unfortunately, not necessarily, I say even not necessarily, almost never the results from the similar algorithms taken from different packages is the same. So you obtain different results depending on the package you use. And that's quite inconvenient. And the reason for that is that, well, when making this kind of processing, we have to make a lot of experimental and statistical assumptions on the problem we are studying. Some of them are, let's say, typical in any kind of research. For instance, the sampling we are doing has to be random. We don't have to have bias, of course. And from a statistical point of view, of course, we have we have to fulfill many hypotheses as independence of the data, linearity, additivity, many assumptions there. And real life is usually not so simple. Things are a bit more complex. But in the case of neuroimaging studies, we also have another problem, is that those many processing steps I have to use in order to obtain the quantitative parameters have many tunable parameters. So I can choose, first of all, which package and which algorithms I'm going to use, but within each algorithm, usually there are several, sometimes many parameters that can be tuned up or down, and the results we obtain are not the same. So to some extent, you can steer the analysis. So if you have a very strong feeling about what's the outcome you expect, and what you obtain after the analysis is not exactly what you expect, you can tune many different buttons and steer the analysis in order to fit your a priori hypothesis. So this is quite a problem, because this might be conscious or unconscious in some cases. Let me show you some examples to illustrate to what extent the results may depend on your decisions. This is a result. Well, actually, it's two results or two possible outcomes of an experiment. In this case, I don't remember exactly where I took this from, but it's an example of volume-based morphometry. So we are studying the comparative volumes of different structures in the brain, and depending on the amount of smoothing I apply in the pre-processing, I can obtain either the green regions you see there or the red ones, depending on whether I apply 4 millimeters of smoothing or 12 millimeters of smoothing. Both numbers are within the limits usually employed in literature. So I could use either 4 or 12, or of course any value in the middle, and it's perfectly okay. So how can I know which is the good result, the red one or the green one? And actually the answer is that there's no good result. So I don't know which is the good one. So I can choose whether I want to obtain large areas, as you can see in the sagittal view here. I can choose whether I want large areas or small areas, and all of them are valid results, and I probably can publish both of them. In other cases, this is something which is in the website of BBM, or the place where you can download the package. And in this case, depending on the specific algorithm for spatial co-registration you apply to the data, you can obtain very different results. For instance, look at this particular section, in which you can see that results are totally different depending on which algorithm you have selected to process the data. And none of them is the ground truth. I don't know which of them is the good one. Well, I know that one of the algorithms seems to be better than the other, but that's all I know. And this leads to a lot of inconsistent results in the literature when using advanced neuroimaging methods to analyze the brain. In this case, well, this is a little bit old data, but things haven't improved since then. In this case, it's a meta-analysis of studies trying to detect areas with changes in volume in schizophrenia. And after this meta-analysis of 15 studies, you can see that there are many areas which were reported in less than, let's say, 10% of the studies. And only about 2 regions were consistently reported in more than 50% of the studies. So this is a lot of inconsistency. Even more worrying is that, as it was published in 2012 in PLOS ONE, for one of the most widely used processing packages, which is FreeSurfer, these authors found out that depending on the version of the program you are using, you obtain different results, and even using the same version of the program but running on a Mac computer or on a PC computer, you obtain different results. So this is actually very worrying, probably you agree with me. And those differences are almost 10%, and 10% is usually the difference we find in our studies. So we are not talking about peanuts. It's not just my opinion. There are a lot of references in literature regarding the problems of the inconsistency of the results. For instance, I've selected here in a few slides, you can see some references regarding the problem of localization in this case, and as you can see, these are not second-order journals. Problem of localization, we can have also the problems because fMRI has many tunable parameters, and there are many papers studying, as they say, what can do and what we cannot do with fMRI, how reliable are the results from fMRI, etc. And also regarding the statistics we apply in order to obtain our results, there are a lot of complaints out there regarding, as it says here, an excess of significance bias in the literature. So people are reporting many more positive results than really exist. So that's quite clear. And well, this guy here, Ioannidis, has many papers in this line, and this is probably an exaggerated statement, but why most published research findings are false. So in the limit, or at the end of the day, there are some neuroscientists that become really skeptical about this kind of data. And this one, for instance, says that neuroscience is, in this respect, using seriously defective methods, and it's producing a profusion of numbers that should not be believed. So this is probably too much, but it's where we are. So definitely something is going wrong here. So now I'm going to try to explain to you what's going wrong and which ways we have to manage this problem. There are a lot of causes of the problem. As I said before, there are many quantification techniques grouped into many different packages, and none of them is the good one. So according to the authors, their package is the good one, of course, and it's not clear for the rest of the world which is better, and the number of packages increases and increases over time. And all those packages have a lot of tunable parameters that lead to a lot of, let's say, false positive findings in the literature. So in the end, this produces a lot of inconsistent results, and finally, a lot of doubts about the credibility of these methods. Particularly, I'd say that this is particularly true if talking about the use of neuroimaging in psychiatry. In psychiatry, you know that let's say, the biological differences underlying the psychiatric problems are much subtle than in the case of other neurodegenerative diseases in which things, more clear things happen in the brain. Okay, so this problem is definitely much more intense in psychiatry than in neurology, so to speak. So let me try to explain a difficult concept here, which is that of the outcome space. So the idea here is that when using these methods, we don't have just one single result. We have a wide span of possible results that it's what I call here the outcome space. So that space is the set of all the possible findings I could have reached using different combination of parameters in my methods. Okay, so this space has a very high dimension because I may have easily between 50 and more than 100 different tunable parameters. So it's a space that have more than 100 dimensions, and definitely the number of different outcomes of my analysis, it's thousands and thousands and thousands. So this is very hard to explore this space, and I'm trying to do here a simplified representation in order to explain you why the landscape of this space is very important. In these representations, I try to show you that with the horizontal axis, the x and y axis represent two of those tunable parameters, any two of them. I may have 50 or 100, I choose two of them, and then the horizontal plane represents the different combination of parameters I can do in order to obtain the result. And the vertical axis represents the different possible outcomes of the experiment, different results, and the likelihood of them. So, in the left case, if I have a landscape like that, I can be very happy with my experiment because there's one result which is much more likely than the other ones. And then if I change anything, then the results are not so credible or not so solid. So this is a very good situation in which I can trust very much my result. However, if my outcome space looks like this one, then you can see that I have many different possible solutions for my problem, and probably none of them is much better than others. So it may be difficult for me to make a decision about which is the real solution of my problem in this particular case. Okay? This is a very simplified representation. Imagine that in real world, each point here is not a point, it's a 3D volume with all those colors, and this is not 2 dimensions, but it may be 120 dimensions. So this is a definitely huge space, which is very hard to explore. There are recent works on how to deal with this problem of different possible outcomes. And in this work, for instance, he explored with fMRI experiments specifically, this guy explored the different outcomes of the experiment tuning different parameters, and he found out, and again this is worrying, that he explored just 35,000 possible results, which is not very much. There are many more, but well, this is a sample of possible outcomes of the experiment. And he found out that 90% of the voxels in our brain can be found significant in at least one of the analysis. So again, this is quite worrying. Are there remedies for this problem? Well, we think there are remedies for this problem. One important idea here is that as a difference with experiments in which you are using, I don't know, flow cytometry or any kind of biochemical parameter, if you get, I don't know, 80 milligrams of glucose, you have 80 milligrams per glucose, and that's clear. In this case, you should consider that there is not just one single result. So you have a span of results, and you have to search in that space which is the more solid or the result which better fits your initial hypothesis. So things are not, there's part of science and there's something of art here too, in order to find the proper solution. So there are some mathematical tools, which is this called conjunction analysis. I'm not going into the details, of course, but there are some mathematical tools to try to combine results that come from different processing ways. The problem of this is that they require huge machines. It requires a lot of machine power, and this is even more difficult and more expensive, a lot of self-criticism, which is something very difficult to find out there. And let me show one example of what may happen. In this case, we were studying a paradigm, which is a very simple paradigm, the classic finger tapping paradigm in fMRI, in which we know what we expect to happen. Okay? We know what is exactly the part of the motor cortex which we expect to be activated. And what we did here is to use four different segmentation algorithms: SPM, AFNI. All of them are out there and have a very widespread use, so none of them is better than the other. And what we did here is to depict in red the areas that are the, let's say, activated areas, depending on how many algorithms they become positive. So, for instance, in the first slide here, this is the area I obtain if at least one of the methods is positive for that pixel. The second picture, I only draw here those pixels which became positive in at least two of the methods and three of the methods, and these are the results in which the four methods were simultaneously given a positive result. So these are, so to speak, the more credible or the more reliable results, because I obtain the same, doesn't matter which is the processing method I use, while all of the remaining results depend more on the method. Okay, so this is the type of thing we can do, but of course, as you can see, that means that they have to process the data many times, and this is quite expensive in terms of of computer power. So the idea of the whole process, or the idea we have about how this should be, is that you, the neuroscientists, have an idea or have a biological hypothesis you want to contrast, you want to test using neuroimaging methods, and probably the best thing you can do is to work in a multidisciplinary environment, so to consult with some expert in imaging in order to make sure which are the best images you can use. And then you can feed those data into a big number crunching machine. You have a lot of images. You have also a lot of algorithms. And if you find the proper combinations, then you can achieve some interesting results, so as funny as those you can see there. So the whole process has several, there are several needs here for the user, so to speak, how to manage, how to acquire, how to maintain those images, which is the proper processing and quantification that has to be used, and how to interpret those results. So in our opinion, this is a process which can be much better fulfilled with multidisciplinary collaboration. What we have done in my group is to set up a system, which is the workflow server, which has several components, some hardware and software components that include some storage for the DICOM images, anonymization of the studies at the source point, and cloud manager of virtual machines. I'm going to explain you this now, and some pipelines and one interface. So the idea here is that this of the virtual machines is something very important, because one problem we have here is that if you have to repeat, or you want to replicate your results a couple of years after, it may be not so easy. Actually, we found a lot of trouble when trying to replicate the results when the operating system is no longer the same, when the versions of the software has changed. And then imagine you are involved in a clinical trial and somebody asks you, okay, I need you to replicate those data you obtained 2 years ago, and then you discover, you find out that you are absolutely unable to replicate those same results. So this may happen also with standard statistics, and also probably some of you may have the horrible experience of not being able to replicate the numbers you obtained or the intern obtained a couple of years ago. But in this case, the problem is huge. So what we've done is to define this so-called virtual machines. So the virtual machines are kind of virtual machine in which you freeze the operating system, all the software, all the versions of the software, and you freeze everything there, and you store that virtual machine in such a way that at any moment you can replicate the study that was initially done, imagine, with a 286 Intel computer with 1 megabyte of memory, I don't know. So it doesn't matter which is the type of machine and operating system you have, you freeze everything, and you can operate again with the same virtual machine whenever you want. This is very interesting in order to have traceable results. And these virtual machines have installed a lot of many of those packages I've mentioned before, and they are very easy to clone and to extend. So what we've done is to define a set of let's say, generic processing pipelines in which we have selected what we consider are the best algorithms from all the different packages. So these standard processing packages come from many different algorithms. We made a lot of tests in order to make sure which is better. And these things become frozen and can be used again whenever you want. And it's also very easy to change some parameters in any of these boxes and to see what happens with the results. This is a pipeline for processing structural images, but there are many, for instance, for processing diffusion-weighted data, for white matter, and so on. So I'm not interested in the details of these specific pipelines. We validated this approach with data from Cybersum. So up to now, well, this is a little bit old, but up to now we have processed about 5,000 different studies. So this is quite tested methodology. And to end up, I'd like to discuss a little bit on some of the problems which are beyond the machinery and beyond the software, which are related to the interpretation of image data. Image, as it's obvious, means localization. So we are using imaging, means that we think that things are happening in a certain place in the brain, okay? And for low-level functions, as sensory functions or motor functions, we know since a lot of time ago that they are very well localized, okay? Since Penfield, we know that this thing happens. But if you move to higher-level functions, the possible localization of those functions is something extremely debatable, okay? So where's the religion in the brain, where's the friendliness, and where are those things? This is extremely debatable. And nowadays, there's another idea. Instead of looking for areas that perform a certain function, we are talking about circuits that perform a certain function. But, okay, this is one step ahead. But as we are going to see, I think that still is very mechanistic. And anyway, even though you accept that there are circuits in charge of doing certain things, it's not so clear to what extent those circuits are exactly in the same place for everybody. So this intersubject homology is unclear, and there are, and we don't know even to which extent this, to which scale those things may coincide. Okay, so, and of course we know that the brain is able to move functions from one place to another. So there is something that may be very wrong with the approach of neuroimages, because we are assuming that things are in a proper place for everybody, and we already know that the brain is able to move the functions to different places. So this is just a stupid example, but that may illustrate the problem. If you have your PC, and I ask you which is the area of the PC in charge of setting the margins of a document, or I can ask you which is the defective part of the PC when Windows hangs up. And you can say, okay, that's clear, there's no defective part. You are confusing software and hardware. So my question for you is to what extent we are confusing software and hardware also for the brain, particularly when talking about high-level functions. And this may bring us to previous times of phrenology and this idea of overlocalization. So to conclude, I'd say that we've talked about the many inconsistencies we can find in the literature of neuroimaging, that the methodology we are using is prone to biases, but anyway, there are possibilities of facing the problem. And although there are still many interpretation issues, I start as I began saying that this is a very powerful tool, but as any very powerful weapon, has to be handled with care. Okay. And the final message is that the title of the paper was not so interesting, but the title is fantastic in my opinion. If neuroimaging is the answer, what is the question? So this illustrates that if you use neuroimaging to confirm solid biological hypothesis, a good tool. If you use neuroimaging to find results and see what happens, then it's a very dangerous tool. Thank you very much.